Hi. Your name? Sergio from San Salvador. Okay. All right. And then apparently Mohammed from Egypt.
No, he's gone.
He's gone. See. All right. You can see that, you know, so this is on right now.
I guess.
It should be on. You can see that there is some ambivalence. It took me a long time to accept this. I'm still ambivalent about it. I hear from people that look at this, that they want me to go on. There are people in other places of the world. Even now, I was on a kind of lecture tour, long lecture tour, kind of world lecture tour, even people in the States. But the thing is, the way I like to teach, I like to keep it informal. And here there is some obvious, right, contradiction between informality at the same time, because as the time goes on, I'll get to know you, and then I know who I'm teaching. This is very important to me. So what I need from you is to ask me questions. And I promise to you, if you ask questions, I can do this in real time. I can teach you guys, because there are many ways that you can teach the standard model. There is a question of interpretation of what I should focus on. It seems that majority of you are into what we would call formal physics rather than phenomenology. Although it's hard to define what we mean by phenomenology. And some years ago, I remember we were organizing a conference here. And it was something on phenomenology. And we were trying to decide what in the world we should call phenomenology. And we decided, okay, whatever it's not strings, let's call it phenomenology. And we were happy. And I remember taking coffee with Narayan, my old friend, that afternoon, and they were organizing a conference on strings. But they couldn't decide what to call strings. Because within strings, there were all kinds of things entering. There were two-dimensional matrix models and so on. So they said, whatever is not phenomenology, we call strings. So you can see that there is a murky area that I like to cross here. And maybe the thing to emphasize, what I want to do, and I'm likely to fail in all the three things that sort of are important to me. One, of course, give you the rigor and the structure of the standard model. But I want you, however, you know, the reason that you learn the standard model is just because it's the established physics and you have to learn it. But more than that, you guys want to learn standard model to have an idea how to go beyond. If you really are serious about particle physics, you want to get a lesson. So I have to go back there. I won't teach it as if it's done today, the way it's done in the books. I'm going to go back from time to time into the history. And not just because of my gray hair and beard, but for us to see how the ideas evolved and how sort of new crept in. And the third thing that I'd like to sort of clear, which is not easy, I find, there is a tremendous confusion in our field that has emerged in the, we had a sort of period of 30 years or more of a total drought. Physics is natural philosophy, as Newton calls it, right? The physics that you and I know and love starts with Galileo and Newton, not with Democritus. It doesn't start with thinking about fundamental issues without being able to actually probe what you are talking about and looking at the facts. Facts, my dear Watson, you know, he would say. And when you go through a long period without facts, obviously there will be a confusion what it means to understand. What is fundamental? What is it that you should be struggling to do now that we have to go beyond the standard model? Okay. I'd like to pay a lot of attention to that. Actually, on this lecture tour, I was giving lectures practically all over the world in the last 7-8 months. I finished some work that I thought it was important, and I accepted an invitation. This was after 5 years of being in a kind of self-imposed exile. And when you go around, you speak of your own work. But I also spoke about the issue that will come here from time to time, about this confusion. And that will actually cause fierce debates, which I like. So this is idea. And in all of this, I have a mission. I want to convince you that field theory is healthier than ever, and that the way to do physics is through field theory and not through string theory. Okay, this I want you to see that if I sound to you as a preacher, there is a little bit of that. So standard model, in a nutshell, right? The standard model is the theory of all the particle physics interactions, those that matter. So, for example, it's not about the gravity. Why doesn't gravity matter? After all, matter gravitates. If I ask you, why does matter gravitate? Why does gravity matter if gravity is actually relevant in particle physics world? The answer is?
It's very weak at particle scales.
Sorry?
It's very weak.
It's very weak, but why does it matter? The only force that you and I see is gravity. You know, we have to struggle a lot to see other forces, okay, that took a tremendous ingenuity.
Because it can amplify to give a large effect.
Because there are a lot of particles in a celestial object, like a sun. When, you know, from time to time it will be good to use sort of numbers to exemplify what we think. So how many particles, for example, in a sun? You have an idea? When we say a lot, you know, there is this always a joke of a student in exam. He says it's big, you know, how big? Very big. Very, very big. So if some idea, tell me.
Well, for the Earth, it's an estimate of about 10 to the power 50, 10 to the power
10 to the power 50, right? The sun should be at some 10 orders of magnitude more. This is a huge number, right? The thing is, okay, as you know, if I write the electromagnetic potential as a function of R, and I could write it as E squared over R, or E squared over 4 pi, the gravitational potential would be, it's G Newton, right? And then if I'm just in Newtonian physics, of course, as Einstein taught us that it's energy that matters, okay? Gravity couples to everything. It's sort of crazy the way it couples to vacuum, couples to nothing, not only everything, but also to nothing. So you have two bodies. This is what a Newtonian potential is, and in the world of untitled particles, right, the scale, by the way, when I speak of scales, I will often speak of large and small scales. So the unit of scale, the most logical one, is the proton mass. After all, that's what makes you and me, right? We have mass because proton has mass. So if I take that m is order of GeV, which is a proton mass, G Newton, do you know in these funny units that I and most of us use, what is G Newton, roughly? When you write it, we write G Newton as one, there are various ways of writing it. Some people put 8 pi, some don't, but roughly, let me call this, I don't want to be precise, m Planck square. What is a Planck in the units of proton mass? Which is why gravity is weak. After you guys tell me that, some of you tell me in your message that you're interested in gravity, among other things. Please, if you're interested in gravity, know the facts about gravity, okay? Because if you don't know the facts, I'm scared you may take a wrong road. For example, one of the things that I'd like to come back from time to time, hearing that you guys are interested in gravity, was a claim that went on for decades. And you know, I studied when I was little, and it went on, and I'm sure you heard it, that gravity of Einstein's theory has to be modified. That is simply wrong. It may have to be modified, but it's absolutely not true that it has to be modified. The beauty of Einstein's theory, which was something that in recent years was pointed out by Hooft and pushed a lot by Dwali, my occasional collaborator, by the way, who was here before he left us, is actually showing that gravity as it is, Einsteinian gravity, may actually work even at very high energies. Okay, I'd like you, at the end of the course, I would like you guys to be able to understand what I mean. Then I sort of will feel that I didn't fail. By the time that you learn gravity deeper and the standard model. But anyway, at this point, G Newton. Well, anyway, and Planck, you don't have to know it, but it's really large. And the way the student would say, very, very, very large. It's about 10 to the 19 GeV. So you see that gravitational force is irrelevant, right? I will get a factor here, which is 10 to the minus 38 over R. And this is why I'm not going to speak about gravity in the standard model course, which is very strange, right? And that's the thing I should be talking about, but I won't, because it doesn't matter. But matter gravitates because, as you said, once I have a number here, which is 10 to the 50, then of course it's going to win over all other forces, especially because the Earth is basically neutral with an extraordinary precision, just like you and me. Okay, so then the standard model is a theory of strong, and V, the only other forces I have in electromagnetic interactions. So you must have heard, I mean, I had sort of lectures of Smirnov on the kind of particle physics. So what is it, what do you know about? Someone asked you in a few words. What is the standard model based on? Just to see if you know something. I mean, today what I want to do, I want to start talking to you guys, okay? Let's say the structured lectures, let's start on Wednesday, or maybe in a half an hour, let's see. But let's sort of gear us there. So I have no idea yet of who you are, really, and vice versa.
They don't like structure, you mean, or what?
I don't know. Tell me what comes to your mind when you say the standard model, what you know at this point, so that I have an idea what.
And if someone asks that what is it based on, I will tell the group structure.
Okay, so there is a group structure. A group structure of what? Or what is the theory based?
It's a Lagrangian.
Sorry?
A Lagrangian.
Lagrangian, of course, will, okay, unlike maybe Galileo and Newton, you and I will like Lagrangians, of course, but we don't have to write a Lagrangian. I could write also the equations. Lagrangian is more convenient, I agree. And Lagrangian possesses a symmetry that Hassan said. That Hassan, but the theory, what is the theory, symmetry? Okay, anyway, the groups are, for the strong,
S3.
SU3, weak,
Electroweak, SU2 cross U.
SU2, and U1. There is sort of something really beautiful that we can see even at the end of today's lecture, that it cannot be the way I wrote it. We'll see that they have to mix. I think maybe, okay, if not on Wednesday morning, we'll be able to see that. Oh, by the way, you want to have a lecture on Wednesday? There is the last lecture or technical lecture of the Salam series.
What is the other?
If you really want to go there, it's sort of on statistical physics, right? It's not high energy physics, and it's going to get technical. So I don't know. In principle, if you guys want to attend it, we could also change the. But if you're not interested, let's keep it.
If we can choose not to attend it, then we will not. If we can choose, because sometimes it is compulsory for us to attend the colloquia and lecture series.
I had fights before with the previous director, and maybe we didn't win. Well, let me say publicly, it's crazy. I remember when I was a graduate student in the States, you know, the boss of the group would tell me, don't go for colloquium, please. I don't want you to get frustrated. Yeah. Because sometimes when people speak over your heads, you feel that you're not that smart that you thought you. Yeah. Because all of us sort of felt smart at some point of our lives, right? That's why you guys are here. But what is this symmetry or what? I mean, there are many symmetries. For example, the first symmetry I saw as a child, I don't know if that's what you saw, was the symmetry between left and right. I was like 5 years old. So this is also symmetry, left-right symmetry. which by the way will play an important role, we'll see. There are symmetries like isospin symmetry, which sort of tells me that proton is similar to neutron. There is something, however, peculiar about these symmetries. They're very different. In other words, what I'm referring to, left-right symmetry, you and I would say is a global symmetry. Isospin is a global symmetry. I use that to sort of classify the world. Lorentz symmetry. But what is peculiar about these three symmetries?
Gauge symmetry.
The gauge symmetries, okay, which actually the language is a little misleading, and so this would be the gauge symmetry. That more and more this is called redundancy. You will see what I mean. I'll try to explain it. Anyway, once you say there's a gauge symmetry, what we mean by that is the following, that I want to make a transformation, changing a phase of my object, whatever it is. For example, this could be a spinner, which could be an electron, or whoever, a quark. And I say that I want to change the phase of that field. And the reason I want to change the phase, I've noticed that the theory that when the electron propagates, if I don't make this as a function of x, I will notice immediately that there is a symmetry. The phase of a spinorial field doesn't matter in the Dirac sense. Well, that's at the end is a conservation of charge, or it could be a baryon number, whatever. So I have a symmetry, and it could be SU3, SU2 cross U1, depending how I write this thing, which will give me a conserved current. It's a true symmetry. But then I say, well, I want to make it node. Is that your name?
Yeah.
Okay. I want to take one value of the phase here and the different where she sits. Well, someone has to communicate between us. There is no way we can have an invariant if there is no messenger. So the beauty of this idea that you promote the phase into a space-time dependent object tells you immediately there has to be a messenger. Or there was a messenger, by the way, you know, chicken or egg, what comes first? It's always a hard question to answer. But the thing that we know that there is this profound connection between what is beautiful about modern physics. What we learned that every fundamental force has a messenger like everything else in life. And that's what makes physics great. So the gauge symmetry is equivalent to the existence of messengers. It must be there. And the number of messengers depends on the group theory, okay, that you know, right? Well, you didn't probably study yet non-abelian, or you did?
No, not in the course.
Not in the course. We'll do the justice to that. It has to do with the number of messengers. The number of these messengers is equivalent, is equal to the number of, so the number of messengers to the number of generators of the group. So in other words, there is one messenger here. And we call it a photon. There are three messengers, obviously, right? And they are
W plus minus and C.
W plus, W minus, and Z. There are three photon-like objects. The only difference, well, there are two differences. W carries charge, okay. So but Z is just like a photon, except
It's massive.
it's quite massive. Roughly, how massive?
91.
91. Okay, you know even precisely. Okay, around 100 GeV. And here there will be 8 of them, and we call them gluons. And it seems that they are massless. Everything indicates. We don't really see gluons the way, you know, we have problems seeing quarks, as you know, we'll talk about that to some degree. Most of my course will be on the electroweak part, just because I have to teach, unfortunately, you know, this course would come normally after the field theory course, but we can't do that because it's 1 year. So I got to teach you the field theory of what is important here. The symmetry breaking, right? There is no symmetry in the end. there is something very different. Z boson is heavy and the photon is not, okay? And that will take us some time. We'll also talk about QCD, and we'll have to, and I'm sure Alexei told you about that, how we see quarks and gluons, so it's in there. Okay, so that much you know, it's clear. So you could say, in a nutshell, you would say, so the fundamental interactions of nature, it's all about gauge symmetry. So if I think of the standard model, I would say that there are two essential features. One is the gauge principle. Let me call it gauge principle if you wish, because the word symmetry may be a little misleading. What I mean, if I make a transformation, psi goes into I alpha psi, where this is a constant, eminator will teach me that there is a conserved current. And J mu has obviously the form that you could guess almost from Lorentz structure. If I now say that I want alpha to be a function of x, I'll get no more, nothing else. There is no conservation law emerging here. So it's not a symmetry in the usual sense. Okay. We'll see what it is. And another thing which will be extremely important, it will be as important, and it's not stressed enough, it's crucial. And I'll do something for you that is normally not done. I will ask you to, when you learn the structure of the standard model and the symmetry breaking, I'll ask you to, for homework, actually a hard homework, to try to construct the standard model in a world in which parity is not broken. And you will see that all hell will break loose. There is a miracle the way the standard model works, and it's not appreciated enough. It's really a miracle. It's magic that way it works. And in order to understand how hard it is, you have to do something. How hard it is, how miraculous that it works. You have to do something that wouldn't work. You see, you can't see the. It's very hard to see magic when it's been there in front of your eyes. That there was something extraordinary, simple parity violation. And parity violation is maximum. It seems. To appreciate the importance of parity violation, you should see the pictures, if you haven't done yet, of Li and Yang when they got the Nobel Prize. They look the way you guys look now. They were a little older. They got the prize like a half a year after it was conferred, or maybe let's say it was conferred by the end of 1956. They sort of suggested the thing in the summer of 1956. Who cares you say 1956? You know, these years don't have the same meaning as they have to me. At the end of the year, the experiments were done by Wu et al. And by Lederman and Carvin. And by October next year, they had a Nobel Prize, and they looked. Why was it so earth-shaking? Because it's such an important symmetry, and you sort of, we all fall into the traps of dogmas. Everything until that summer was always symmetric in physics in general. All the fundamental literature, everything you look at was symmetric on the left and right. It would turn out that the weak interactions are completely asymmetric. Since we are still sort of at this point, how did they see parity violation? Can you remind me? In weak interactions, after all, weak interactions, just to remind ourselves, is the discovery of a neutrino, right? The necessity to introduce it is a neutron decay. So what happens is I have a nucleus that decays. So how will I see parity violation? If some recollection what I did.
If you have an atom with a nucleus which is spinning in one direction, then you polarize it. You polarize it. So
that you sort of have a sense of direction, because the guy is sitting there, so you can't say what the direction is. So the thing that is useful to you polarize, So imagine that you're polarizing the neutron, actually. You polarize cobalt 60. So now you know this. You can call this left or right, whatever, okay? And then you will have two possibilities, that electrons go up when they are along the lines. Of course, they can also go in different directions, but along, say, the z-axis, and antineutrino going down, or electron going. In a symmetric world, you would expect the equal number, right? If there are 100 electrons coming out, 150 of them should go up and 50 of them should go down. It turns out nobody goes up. They all go down to this day. I think what we should do then, by the way, it's when you do this three-body decay, it's not so easy to see what is going on. It's much, much cleaner when you do a W decay. It's a two-body decay. So actually we can have that as a homework, or maybe we'll do it here, we'll see. You can compute everything and see explicitly. It's a fairly simple calculation. In the limit, of course, here it's even nicer because the approximation that I use here, is that these guys are massless. This is a very good approximation here, you agree, because W weighs, you know about weighs, so this is 40, at the rest frame of W, this is 40 GeV. This guy anyway is basically massless, okay? When you think of neutrino, you can think of it in first approximation, it's massless. It's only massive if you go deep down and start for some reason to be interested in this fundamental issue, okay? Why do I say that? Electron mass, of course, is MeV, half MeV. What is the neutrino mass in those units?
Less than
0.1.
Less than 1 MeV, right? So you see, even million times less. And that means billion times less than the scale. And our scale, we said, for the rest of the course, is going to be GeV. Well, okay, maybe it's not fair. In this sense, it's not fair to compare it. You see here, maybe I'm a little teaching, because proton is not a particle, right? So it's not fair. Okay, just like you and I are not particles. Not in the sense of elementarity. It's a bad. So maybe it's more fair to compare with electron. But anyway, here at this point, okay, they are massless. So when they are massless, then the only thing that matters is helicity. So maybe I could start with the before we go, why not start with the gauge principle? The way developed, by the way, it's sort of like the kind of most natural rule. This is the way science ought to progress. And when you skip that, I think you are making a mortal mistake, okay? So let me put it once again. If field theory is something that works beautifully and you decide to abandon it, then you are making a mortal mistake. I've been saying this for decades. You should never abandon the language that you know. Don't learn Chinese by abandoning your mother tongue, okay? Learn it, but not by abandoning your mother tongue. You will see yourself, you express your better yourself in your mother tongue. And especially don't abandon the techniques and tools that work perfectly. In the 50s, as you know, the thing that emerged that defines the great success of particle physics is the late 40s, early 50s, is QED. If I write the Lagrangian of QED, let me write it first. So I will write the kinetic term for the photon that was there, I knew. Then I would write the kinetic term for the electron. maybe I call it, well, for some fermion that carries charge, right? So in this case, I write a Dirac-Lagrangian. Kinetic for the photon. And here, let's say, any charge. It turns out the interaction was established the way the photon comes, where F mu nu is the usual electromagnetic field, that I can write as a function of a potential. It turns out that the photon couples to conserve current, which has the form here. Q is the generator of electromagnetic charge. It's just a collection of charges, right? What I mean by this, when I say, I mean that QF is some number Q. For example, electron Q for the electron would be, I just write like this. Q of the electron is -1. Q of neutrino is 0. Have any idea to what precision? The charge of neutrino is very small. How small? Very, very small. You don't see. You have some idea?
No, I don't know. I don't want.
1 in 10, 1 in 100. You know, because you will always hear yourself saying that neutrino is neutral. You know, we are so used to say that. Okay. And actually, that's one of the things that we can say with a good deal of authority. It's in 1 in 10 to the 20. Okay. The quantization of charge, that miracle, this incredible thing that we will be sort of, here in this course, you and I will have to accept it, but we should keep in mind that this is the question that we can ask in particle physics. You know, imagine all of us here in the room having our weights, integer numbers of your mass. That's crazy, right? It's a miracle. Something has to be there behind this. For example, Q of the up quark, 2 over 3, and Q of the down quark. Okay. This is what makes the world, right? Well, the neutrino doesn't even make the world, it's just observing it. You probably know that there is a photon C, right? That we might background radiation. No, all that. There should also be a neutrino C.
How do you get the experimental bound for the neutrino charge?
For the neutrino charge, how do I get this bound on this? This is similar. This is similar. It's the same thing to get the bound that this is 2/3. To what precision when I say it's 2/3? Because you would not expect an integer number, right? In other words, all the charges are integers. How do I get this information? Let me come back to that. If you don't mind. I don't want to digress now. It's a fundamental question. I promise I'll come back to that. But please notice it's the same thing. The miracle is already here. Not just here. Right? The charge of the electron. And remember, please, that there are no fractional charges, as we often say, right? This is just the funny convention I've chosen. I've chosen to Q electron to be -1. I don't know why. Well, you know why. There were no quarks at that time, so it was obvious that it was the charged particle, you give it the charge 1. So notice how I can speak about this. This is the conserved current. And this is of course this is just the Maxwell theory. At this point, it's just a classical Maxwell theory, right? Written in a convenient Lorentz covariant language. And here I just go and notice, okay? I have now 2 approaches. The first thing is that there is a symmetry here. If I perform this transformation, see, I'm keeping this here, just to remind myself when I change the phase of my charge fermion, I will change it depending what the charge of that fermion is. For example, neutrino will not fill. This is just to remind myself. A neutral particle will not be transformed under the charge transformation, obviously, right? Okay? So I keep this. So what we say that this Q is a generator of U1. It's a generator of U1. You see, I'm generating a unitary transformation e to the I alpha Q. Just the way you would generate the SU2 transformation with 3 generators, Pauli matrices. Okay. Notice, in the case of U1, there are no commutation relations, and therefore this should be a continuous number. Right? Just to remind you that the miracles do happen in non-abelian. Let's talk just of the global one in SU2, right? How do I write the SU2 transformation? I write as I expand in 3 different rotations around the x, y, and z axis, right? So I have 3 Euler angles, and at every time I have a generator of rotation TA, TB, do not commute. By the way, I'll be insisting a lot on SU2. I'd like you to, one thing that I would be happy, even if you don't learn much about the standard model, that you know group theory when you walk out of my course. I know you think that you know it, and most of you probably know even a fancy group theory, but what I find out generation after generation, even when you know fancy group theory, you don't know it in your fingers the way I'll try to show you what I mean by that. Because everything is SU2. If you know SU2, you know everything. You know Lorentz group, it's all about Pauli matrices. If I go to a bigger group, right, I just put some funny FABC, that's all. But I build it with the generators of SU2. And TA are Pauli matrices, right? Normalization is the one. And you know, for example, that sigma 3 is 1, 0, 0, minus 1. So notice charge now is going to be quantized. And this is what we call charge half. We used to call it spin, right? In quantum mechanics, we always did up to now spin. If I had another bigger representation, right, this will be a doublet of states, spin half, spin minus half. How would a triplet look like? So this would correspond, let me erase this. Right. So the what did I erase? I can generalize SU2, as you know. The groups get generalized to an algebra. So whatever satisfies this algebra, I call SU2. I'll be very careless about, as usually, particle physics stuff. You and I are going to care in this course only about the small transformations, small rotations, if you wish. So it won't make any difference whether I call it SU2 or not. Because now I can go to the situation you just said when T3 is 1, 0, minus 1. Notice it's twice. In SU2, charge is quantized. That's a miracle of commutation relations. In any non-abelian symmetry, in SU3, you did SU3, I presume, right? What we call Gell-Mann version of Pauli matrices, okay? But here in U1, there are no commutation relations. So the fact that I get integers here, it's really amazing. with this precision. So, if I perform this transformation, I'll find out, as I wrote before, that that current is conserved. The d mu j mu is 0. And the photon couples to a conserved current. The thing is, it's very easy to see here that I can promote alpha to space-time variable. It's obvious why, because of the form of f mu nu, I can, as long as a mu transforms is a mu plus 1 over e d mu alpha. It has 1 over e because I put e outside, okay. It's the way I written it, okay. This is the famous, so the way this minimal, the Maxwell theory, the way it behaves, it has a gauge symmetry. The thing, of course, this is a little digression, okay? Just forget about what I said here. If it was anything, it was quick. I can actually reverse this, and I can say now, okay, this is sort of being smart, want something work. I can say, well, let me promote this as a principle. In other words, I start with the Dirac-Lagrangian. This is what I said here. I start with this, which is obviously the symmetry under the redefinition of the field. But I want to now make a different different places. Then when I find out that if I started with this Lagrangian, I will have to modify it. D mu would become what we call covariant. In other words, I would have to introduce a field in order to compensate for this transformation. I have to do it if I do this. So by asking this, I'm asking to it. And that's what somehow, promoting this into a principle, it's sort of what lies behind the great success of what is today's particle physics, the Sander model, okay, we'll take it seriously. Why do we do that? Because of the way the QED worked. It worked miraculously. You know, it's the best tested theory of science, which agrees with experiment to 10 digital places. It's miraculous. So what you want to do, what you and I want to do, by the way, we should always take it as a principle. We are just going to try to imitate what worked before. And don't change that. And let's see where it takes us. I'd like to do that at the end of the course, to try to see where I could take you for the next step, and whether we would fail or not. So in other words, I can write the QED Lagrangian simply is the photon kinetic energy plus now f bar gamma mu d mu f is the same thing, but it sort of hides and minus the Fermion mass. And since it worked so well, okay, but what was the thing that worked, okay? The thing, of course, was crucial that there was a conservation of charge. It was very important to start with the symmetric theory. Charge is conserved. And therefore, if you wish here, photon couples to a conserved current. That's crucial. This gauge symmetry is fundamental, okay? What it does, because it's not really symmetry. Why is it there? Why is this thing there, really? And the reason is obvious. I'm working here with a 4-component mu. I'm pretending that there are 4 independent fields. Now, why am I doing that? I want to have a Lorentz covariant formulation of my theory now that I know that I want to describe physics when my particles move fast. So when Einstein told me I have to use the Lorentz covariance, and this is very convenient, but this is not physical, right? There are unphysical degrees of freedom necessarily. How many can be physical? How do I know that? I knew that from the time of Maxwell. After all, from this Lagrangian of Maxwell, what you knew is that divergence of E is rho. Curl of B is J, the current, where this is J0 and this is the... so what I have 3 degrees of freedom for electric field and 3 degrees of freedom for magnetic field, apparently 6, but then there are constraints, right? Because delta B is 0. Well, that's what we think. I mean, here is an interesting point. What if it was not? From time to time, I'm gonna mention this amusing possibility. How would the world look like if this was not 0? It's not easy to work. It's not easy to work it out, but the consequences are extraordinary. Another question is, what if there are magnetic monopoles? By the way, some of you wrote that you like to do, and I think all of us, but the people that do particle physics, we sort of feel we would like to work on fundamental issues. We often say that, especially the people that we meet outside. It's not easy to convince each other that we work on fundamental things. You know, when we give talks, we give hell to each other. Someone comes and tells me they're working, she or he, on a fundamental thing, and I may feel, no, it's not fundamental at all, and there'll be a debate. But how do you know you're doing something fundamental? Well, go to a party, or go to the bar, and you know, when you're asking coffee, try to tell them what you're working on.
They get interested.
And if you say that you are working here, that you think that there is a magnetic monopole, everybody in the world will understand you, because every child tried to break a magnet or try to understand this crazy thing. How come there are no poles? There should be a test. Not by working on very complicated things that other people tell you are fundamental. Okay, go and try to tell this to a cashier, and you know, she won't even serve you. And there is another constraint, right? Which is vector light. I'm writing this not in a, okay, this is high school stuff, basically. Sorry, just to remind you, there are 4 constraints. There are 2 actually physical degrees of freedom. In the case of photon, these are the transverse polarization, right? So that means, of course, that I can't work with this Lagrangian. I need to sort of, you know, it's like introducing a Lagrange multiplier. I have to reduce the degrees of freedom. And that means to, what we say, break the gauge. Break the gauge freedom, right? I just reminded you to see that you can't write the propagator. So we add a piece here to this Lagrangian, which is, I think I wrote it like this, right? By the way, you could play with these equations. You can write down now the equations of motion. I won't do that. And you can easily convince yourself that the box of d mu a mu is 0 for any psi. And if something is 0 everywhere, then the box of that thing is 0, then this vanishes. You can just take it to be 0 at infinity. You want your fields to be well behaved. So actually this is equivalent to what normally you are used to, right? In order to reduce the degrees of freedom, typically you fix the gauge, and or in this particular gauge you would get the following thing. Now, why you knew that there was a problem? There are various ways. One is counting degrees of freedom. The other thing is, if from here, if you write what the momentum is, right, which is the Lagrangian of dA mu dot, this is F0 mu. But notice that pi 0 is then 0. Okay, obviously A0, for example, is not a physical degree of freedom. There is no time derivative of A0 and so on and so forth. So there are various ways of seeing it, okay? And we cure it by fixing the gauge. In other words, we work with extra degrees of freedom. This will turn out to be the crucial thing that will make the standard model work. This trivial thing that I will repeat maybe ad infinitum was what made the genius of 't Hooft. 't Hooft was the guy that made the standard model work after years of struggle. For example, both Weinberg and Salam failed. They forgot this point when they were trying to do the same thing for a W boson. You will see what I'm talking about very soon. Is there anything you want to comment or ask me here? Okay, as I'm sort of going over the very basics. One side, maybe just to remind you that from here, the propagator, what you will get is, with our convention, is minus I over Q squared. You remember G mu nu, like psi minus 1 Q mu, Q nu over Q squared. And it's particularly nice. Confront this is the photon propagator, the propagator of the scalar field. You remember the propagator of the scalar field? Would be I, notice a different sign, over Q squared. If it has a mass, there will be minus m squared, right? This is the mass is a pole of the propagator. So notice that if I take psi equal 1, I have a simple interpretation of what is going on. Typically the 4 polarization tensors. Imagine a photon moving in the z direction. This was not the formula here. Typically we choose A0. And then there is A12 or A plus minus. The transverse polarization and longitudinal polarization. Sorry, this would be epsilons. Right, where A mu is just an integral over epsilon mu of P e to the minus I px. Over P. The polarization tensors that you know. You would easily see that this is the sum of the polarization tensors. I'm not teaching this. This is some telegraphic recollection of some basic fact. Sum of epsilon mu star would be minus G mu nu. So that actually I could write the photon propagator. This will be written as plus I over Q squared sum over epsilon mu star. Notice why I had a minus sign here, because what I have is just like a scalar propagator, only I have to sum over all the degrees of freedom that are propagating, okay? I'm propagating this physical degrees of freedom, okay? When I'm outside, when I'm doing the scatter free photon, it's not gonna carry these unphysical degrees of freedom, but they can propagate, right? We are So just to remind you why there is a minus sign here. Okay, the I components which are physical, the transverse one, should have plus I over Q squared. We have to have the same convention for the propagation of a particle, right? And the same should be for the spinner. We'll comment on. Okay, but anyway, you are checking the propagate and you find out that everything is well defined once I fix the gauge. What is crucial for the photon is this dependence, and not just for the photon. Look at the scalar field, 1 over Q squared. The fermionic propagator, which we often write. Do you remember the fermionic propagator?
Yes.
I p slash minus m, which is I p slash plus m over p squared minus m squared. Now, if you remember, p slash over m is sum of the polarizations, sum of the states, the electron going this way, okay, in this case, when I exclude the positron. Just to remind you of the convention, sorry, why did I put Q? It should be Q. So once again, it goes as 1 over the momentum or energy. This is very important. This is what makes the theory work. There is this fancy language that we use, you know, it's all about language, choice of language. We say that the theory is renormalizable QED. It just what we should say that it makes sense, that we can compute. Renormalizable means I don't get infinities when I compute scattering amplitudes. Okay, it sounds fancy, but obviously you don't want to work with something that is infinite. So a typical thing that you have to compute in QED, right, is that everything is in Feynman diagrams. So when I want to scatter electrons, I just exchange the photon, right? So I have typically a diagram like this. But what I have to do, since I don't know how to actually compute the process, I do perturbation theory. And I'm lucky because although E is not small, E is about a third. So my perturbation theory would fail if I was not lucky. The expansion parameter actually is this, which we called. And this is roughly 1 over, well, let me write roughly 1 over 100. Turns out that these constants, complete constants, are not constants, right? You may know that. They presumably don't vary from here to there, where Victor sits. But they do. I'm sorry. They don't, hopefully don't vary time. But they do vary with energy or with distance. But, so, you know, normally we say 1 over 100 is 37. That's for very small energy. Anyway, roughly 1 over 100. We say that the complete constants run. You heard this expression? Yeah. With energy? Which is a terrible expression because they really crawl. It's a logarithmic change, which is very hard to see. But anyway, this is when you get enthusiastic about new. So I have to compute diagrams like this. Sorry, another photo. Gamma or ray. So how do I compute these diagrams? This you know by now, right? Although probably you're not doing it yet. Right, but what I have to do, there is a propagating momentum here called a Q. What I have to do is integrate. I have to integrate over because there is one momentum which has nothing to do with what is going on, right? There is a momentum here that is conserved. P1 plus P2. P1 plus P2 is P3 plus P4. But there is a momentum here, of course, which has nothing to do with the, for example, the momentum of this guy. Then there are correlations. There is a flowing momentum which I call Q. Obviously, that has to be integrated over because I can propagate photons with whatever momentum as long as P1 plus P2. All I have to remember is this. And then I have to write my propagators. Right? This is what Feynman taught you. Just like the thing that you do at the tree level. You haven't started doing this yet. Or you have. Who's teaching field theory this year? Sorry? Ah. So you started already, or?
Where at that?
In the course, he has not done any loop calculations yet.
He has not done it yet, right? It's an early, but you do know that you do that, okay?
Yeah.
It may not make much sense today, but please remember it, and we'll come back to it. Take my word for it today. That's all. This is all you have to do. This is what renormalizability is all about, the field theory. And I want to get a finite answer. If I compute this and I get an infinity, I better change my theory. So it will work only if the propagator, I integrate over all momenta from 0 to infinity momenta. That means when I go to very large momenta, my integrand has to vanish. Period. So it will work only if the propagators go to 0. And they all do. And this is why it works. There are two things that make it work. The nice behavior of the propagator of the photon. The gauge invariance will take you to something that is called ward identities and so on. This will be a technical, very important issue here. But for you and me, what we have to know in a nutshell, just the thing is, when I integrate here, this will work only if my propagators vanish at infinity, okay? And they do. And you can already anticipate the problem. I don't know where you are. There is a problem number 3 in the homework when you have to find the propagator of a massive gauge boson. Did you compute it yet, any of you? That's via, okay, it's not, we'll talk about it maybe after you finish your homework. Well, I can cite it on Wednesday. So now, this worked for me. And I decide that because this is successful, I want to use it for weak interactions. Now the thing that is, maybe let's say I guess we are starting now to be structured. We could start as well. It all starts with the Dirac-Lagrangian. I was watching recently videos of Coleman. You guys know the name is familiar too, right? He was a great physicist, but maybe as great as he was as a physicist, maybe even greater as a lecturer. So he has a beautiful lecture on quantum mechanics. It's worth saying he was also a stand-up comedian. I've very few times in my life seen someone that good. I remember him, he got the Dirac medal. We couldn't stop laughing. I was just, well, you had to understand he spoke with a strong New York accent. I lived in New York for many years, so maybe a lot of people didn't appreciate it. It was always a joke after joke after joke with him. So Coleman has this talk on quantum mechanics. He writes first formula. He says, anybody here who doesn't know this? And he sees someone raising their hand. Oh, he says, please leave immediately because you will not understand anything else. Okay, someone won't be helped. So if there is anybody here that doesn't know this, please leave immediately, okay, if I may use Coleman's joke, because that you won't profit from my course if you don't know the Dirac-Lagrangian. So what the right does for us, of course, what is F? Is what I would call the spinor, which transforms as a spinor, where lambda is e to the I theta mu nu sigma mu nu. And then I don't have to write everything right in the homework. With our conventions is 1 over 4 gamma mu where my gamma mu's are 0 sigma mu plus sigma mu minus 0. Okay, where sigma mu plus minus is 1 and plus or minus sigma. As I promised, it's all about Pauli matrices, right? It's nice when you go to a two-component notation that you realize there is nothing else but Pauli matrices. These are generalized Pauli matrices. I put to 1, I'm cheating a little bit, okay? The Lorentz group, it's not like SU2, right? There are boosts which are different from rotations, okay? Then I can generalize. So, when we say that it's a spinor, actually, what we mean is we introduce a gamma 5, which commutes with all the sigma mu nu's. That's important because it's anti-commutes with gamma mu. And my gamma 5 would be this one. Some people have opposite sign of gamma 5. But then also what they do is and that means that for me, I will define left and right projectors to be 1 plus minus gamma 5 over 2. So notice my left is 1 plus gamma 5. Actually, I hate it because in the notes that I've sent you, I've used there 1 minus gamma 5. Actually, they were written in, they was transcribed by an ex-diploma student, Alejandro Melfo. And I think she was using 1 minus gamma 5. Anyway, I'm not consistent with myself. But it's very important that you remember this. A lot of people think that somehow the left-handed in Misa should be 1 minus gamma 5. It's called V minus A theory, I'll remind you. That's nonsense. Because gamma 5 is defined, oh, I forgot, gamma 5 square is 1. Gamma 5 itself sign is not defined. So left and right cannot be defined in a convention independent manner because gamma 5 is not. If you like that left is 1 minus gamma 5, just take gamma 5 to be minus my gamma 5. So this will be gamma 5 Goran. And gamma 5 Hassan, if you don't like that, take a minus sign. And then you like this one, okay. What it means, that means that I have I started to use it. So FL would be LF. This is what I mean by FL. And this would be and I should have written here, it's a 4-component. We have to come to this issue, as I promised, but not today. QFL is LF, so my F is obviously UL, UR. Notice L projects an upper component, so this will be UL0. So when I tell you that the spinor is left-handed, it's also I'm telling you that it's sitting up there. And the right-handed guy is sitting. And that's trivial at this point. It's a little less trivial. It's a little less trivial when I remember that if F is a spinor, FC is also a spinor. That's what you have to show. FC is CF bar transpose, where C is defined the usual charge conjugations through its I can take this to be I gamma 2, gamma 0. And I will. So this is I gamma 2 F star. Okay, notice what I'm saying, that charge conjugated spinor, of course, now you know, it's going to be a complex conjugated to your field, because remember what I did? I defined this F transforms. You see there was combination alpha Q times F. I can put also small q, remember, it doesn't matter. It's just a number. Then the complex conjugate has an opposite charge. You know, this is this incredible thing, by the way, that came out of the Dirac equation. That took him by surprise. And I have a great nostalgia of that era. Some 10, 15 years ago, Bjorken, you know who Bjorken is? The father, one of the main fathers of quarks after Zweig and Gell-Mann. He got a Dirac medal and he came here. And he was very worried. He gave a beautiful talk. And he was talking to you guys. He was worried to speak to young people. He was really worried that what disappeared in modern physics was a fear factor. It was crucial in order to do good physics. You see, at the time, I have a nostalgia for that era, although it's much before my time. What you said mattered. So you were very, very careful about what you said. You see, Dirac writes his equation in 1928. He takes 3 years to say publicly. He sees immediately that there must be a positron, but he's scared to say that. What if he's wrong? Your reputation depended whether you were right or wrong, not whether someone said that you were smart. You couldn't go on preaching year after year, decade after decade, that this is the direction to do physics, and nothing is seen. People laugh at you. You know, Pauli was scared. Pauli never wrote a paper on neutrino. You know that? He wrote a postcard. He was very, very scared. And later on, he actually apologized. He violated his fundamental principle. You know, you would give a talk and he would tell you, it's not even wrong. When he thought that you couldn't see that, okay? A neutrino took a long time to be seen. So, the thing is that FC, this antiparticle, notice the change is chirality, what we call, okay? This is a chirality, left and right. And how does it change it? Take this one, take UL, for example. What happens if I take FL? See, I have to put the bracket to know what I'm doing. If I write FLC, it's not clear what I'm doing. Am I seeing first, or am I L-ing first, or whatever? Seeing in there. So I take FL. So this would be FL, sorry. So this would be 0, I sigma 2, minus I sigma 2, 0, UL star 0. Agree? Notice that this became right-handed. Just like the mirror changes left into right, this incredible thing that I remember all my life. I have this particular thing, okay? I've been obsessed. I've been working on this thing about left-right symmetry, okay? Because to me it's the crux of everything. And it is. No, I'll convince you that for sure. I'll convince you that it's all about left-right symmetry. You will see both the great success of the Standard Model and its main failure. Standard Model failed, fortunately. It did fail when it comes to neutrino. Fortunately. It's not going to be about left-right symmetry. You will see. So this is very important, that the particle and antiparticle have opposite chiralities. An antiparticle of a left-handed electron is a right-handed guy. This is, in a sense, you know, what you kind of, it's not surprising. I can work with left and right, or I can work with electron and positron. This is very important. Another thing which is very important here is helicity. So let's take the case when m is 0. So what I have, of course, from Dirac-Lagrangian, I get I gamma mu d mu f is mf So if I write that f is well, f of x is integral of f of p e to the minus ipx, I will have p mu gamma mu. Let me write the same f, is mf. It's a function of momentum, right? I have my Dirac equation. It's interesting to see what happens at the limit when this is 0. So I'm interested in a situation when I have very energetic particles, or maybe massless. Now it seems that there are not easy to find massless fermions, right? Neutrino gave in. It took some time. There is this incredible thing that I find mind-boggling, which is happening continuously in physics. When something is very small, people start feeling that it should be 0 then, that it will be more natural. It's very strange because 0 is smaller than small. So if you think that small is very unnatural, how can 0 be more natural? I find this crazy. But by the way, when I started to talk about neutrino mass in the 70s, very few of us, I was told I was wasting my time because neutrino was massless, everybody said. Look, it's so light that it has to be massless. By the way, typically when you take some parameter going to 0, you get more symmetry. For example, if a fermion mass goes to 0, what symmetry do I get? I get a chiral symmetry because left and right, of course, they don't commute. Why? Because what I wrote, F bar F, now I know, is FL bar FR. So when mass is to 0, I can now rotate left and right separately because, of course, kinetic energy treats them separate. These are irreducible fundamental quantities. A free guy without a mass will continue moving. A left-handed guy stays left-handed forever. So you get a chiral symmetry. You can separately rotate left and separately rotate R. Then you say, oh, but then the symmetry explains why it's massless. The same way that people often say that it's gauge invariance that explains why photon is massless. Okay, that's a lousy argument. It's the other way around. You're confusing the cause and consequence. And it's worth mentioning here, you know that modern experimental particle physics was a lot about looking for proton decay. In the 80s, people were told that proton would like to decay. There is something we call grand unified theories. They say that proton decays. You and I decay. So my ex-colleague at Brookhaven and Goldhaber Maurice Goldhaber was a distinguished experimentalist who lived until the age of 100 and was active until the last day, a great physicist. He's actually the person who measured the helicity of neutrino. I never understood how he couldn't get a Nobel Prize for this extraordinary thing, but anyway. He and Reines is the guy that discovered neutrino. Imagine we have two great physicists, okay, which most of them deserve Nobel Prize, one got it. They go to the funding agency and they say that they want to measure proton lifetime. But the funding agency says, but you're crazy, proton must be stable. He says, how do you know that? Actually, he was the guy who noticed the first very, very strong limit on proton lifetime. And it goes like this. If you and I decay, radiation would kill us very quickly. Unless the process is very slow. Okay, remember, radiation is not good. Don't be convinced to take a CAT scan for some small injuries that, you know, the hospital may want to do. I remember a few times I tend to get injured when I do sport. They actually wanted to do CAT scan on me with no reason. That's a lot of radiation. It's like months of being exposed to dangerous radiation. And he put a limit, tau p, bigger than 10 to the 18 years. So people said, well, it's so big, then there must be a symmetry behind that. And they invented it immediately, a baryon number, they said. Baryon number will be conserved. Now they said because baryon number is conserved, proton will be stable forever. But he says, but that's what I want to measure. I tried to dig it out. By the way, it's published, this beautiful interview. We used to talk a lot about, with Maurice, about the wrong way we are educated very often. But he said, look, it goes on, but it's stable. But how do you know? Well, because baryon number is a good symmetry. How do you know? But look how long proton lives, and so on and so forth. Now the limit went up to 10 to the 34 years. And yet most of us believe that proton is decaying, and people want to look for it, okay? It's interesting. Because if it does decay, forget about baryon number being an exact symmetry. Even if proton decays, I want you to remember that. Baryon number will be used for symmetry as a bookkeeping. Who cares whether something is zero or almost zero? Isospin is a very useful symmetry that doesn't require that proton and neutron masses are the same. Please remember this, I'll be emphasizing this. Don't get, I may even cheat on you by telling you that I'm predicting something, but actually assuming it in a funny language, like this. So anyway, what we can see here immediately, we'll get an equation like this: 0 E plus sigma dot P, E minus sigma dot P, 0 UL, UR is 0. Remember my Pauli matrices, 1 and sigma dot P. So, no, I'm sorry, this is minus sign because I have P mu, gamma mu. This is lower component of the momentum. This is very important, this convention. Once I decided what is left and right, I have to be consistent with myself, okay? I decided to go left where my heart is, and then I have to be careful. I can't then sort of forget that I did it, okay? So from now on, this will be crucial. And it's a nice way of checking our calculation, which means that E acting on UL or UR is minus plus sigma dot P. U left, right. So let me define this. I'll define it by energy. Forgive me if I do this. This is the equation we got. But what is this? This is the, so I defined by 2, the privilege of the blackboard. You've done this before, I hope. Anyway, the homework, so to remind you what left and right fermions are, I'll come after we finish the homework, we'll comment that. Sigma over 2 is spin, and P over E is just P. It's a directional motion, right? Because the guy is massless. So we just proved here that with my Pauli with my gamma matrices, Dirac matrices, the helicity U left right is minus plus a half U left right. I should finish, but let me just say this. I hate when I go overboard even, but this will just take a minute. When you told me that I should polarize a neutron in a decay, and usually the momentum here is large when you have the nuclear, the momentum transfer is large enough. But just think, even if that's not convincing, we will do this, it's even better. Imagine that I can polarize a W boson. I catch it, I stop it, and I polarize it, okay? It's not trivial, but imagine I do that. Then what will happen? Electron can go up, you agree, and antineutrino could go down, or electron could go down, and antineutrino can go up. Now, notice if electron goes up, where should its spin point? It's massless. I'm assuming that m electron is m neutrino 0. All I'm assuming it is which is a fantastic approximation. This guy weighs 10,000 times or 100,000 times more. Okay, so this is surely 0. So I have to conserve the angular momentum. There is only spin because the guy is at rest. So where should this point out?
Down to the left-handed part.
No, in order to conserve it, this is 1. Just bear with me just for 2 minutes. This is 1. This should go up, and this should go up. This should go up, and this should go up. I have no choice. This has to happen in order to conserve the angular momentum in this thing. There is no, or there is only spin along the z-axis. They're moving along the z-axis. What would that mean if spin is pointing up? That the guy is right-handed, right? Well, this is antineutrino, so. And this, of course, would then be left-handed, which is okay. An antiparticle, remember, so if the interaction is right-handed, the antiparticle would be left-handed. That's okay. In this case, that means that the electron is left-handed, and this guy is right-handed. This is what is seen. In a WDK, I show you a picture. It's beautiful. It's much cleaner than looking at some murky nuclear decay or cobalt-60 when you have a complicated three-body decays. You'll be able to do the calculation, okay. So this is the celebrated proof, experimental, of parity relation. What it means, what it really means, that when you write the Fermi theory, you remember Fermi theory? I stop here. The current must be left-handed. Only left-handed particles. Don't be confused by calling this guy right-handed. The neutrino is left-handed. Okay? So this is 1956, when it was, okay, and WDK came later in the 80s, okay, 1956, at the end of the year, they established that this was happening. It took them a year. It was amazing what a great era it was, okay. I'll remind you what is happening in the 50s and 60s. It's mind-boggling, okay. Young Mills was done, for example, around the same time. There were another thing. Marchak and Sudushan showed that the current is purely left-handed, and it has the form of the actual current. So in other words, J mu would be U bar gamma mu d plus nu bar gamma mu electron, and it has to be left-handed. Everybody has to be left-handed. Okay, the V current, remember, changes neutron into a proton or a down quark into an up quark, an electron neutrino. This is what the course will be all about. Okay, I have to finish here. Okay, I prepared the thing that will already on Wednesday. I'll give you an indication, or we will be struggling for weeks then later. That I have to do some non-trivial gymnastics to make it work, because if I want to imitate Feynman and these guys, the success of QED, and I want also the W to be a gauge boson like a photon, in other words, instead of Fermi theory, I want to couple a current to the gauge boson. I have to sort of live with that non-trivial problem, only left-handed guy coupled here. But photon, of course, couples to both left and right. And that's going to be highly non-trivial. Okay. Sorry, I took a little more time. I'll remember it next time.
It's still difficult.
Well, maybe if there are public questions, we can still, depending, then we can have the possibility for private questions. But now that we are. Question, comment, whatever. I don't want to lose you in the beginning, okay? So today, since I wasn't really giving you an organized lecture, I said things left and right. When we make sure that nothing escapes. All right.